The Wolff-Kishner reduction is another nitrogen nucleophile addition to aldehydes and ketones, and it's a method of actually removing the ketone altogether. So here's the general gist. We take a ketone or an aldehyde, we react it with hydrazine, which has been used as rocket fuel in the past. It's kind of an interesting molecule. It's got a lot of nitrogens in it and some hydrogens. We do this under acidic conditions. So let's use acid catalyst again, and we end up with, as you might expect to start with, the imine version. Here comes the Wolff-Kishner part. Wolff, I should say, and Kishner were two European scientists who, I don't think they worked together to develop this, but they developed similar reactions at slightly different times back in the 1800s. So KOH and lots of heat and probably some water will essentially allow us to make propane plus N2 gas and some waters. So we'll just put water here as a byproduct as well. So that's a pretty interesting reaction. We don't often see productions of alkanes or an easy way to get rid of the carbonyl group. So this can be a very useful reaction in your synthetic toolbox. So let's go ahead and look a little closer at this. I'm going to just abbreviate the imine formation, of course, because we just looked at those mechanisms. And I'm going to draw the hydrogens here with their NH bonds so that I can use them in a mechanistic steps. So the first thing we're going to do, and as you'll see, this is a reaction that's basically a whole bunch of proton transfer steps. So we're going to remove one of these hydrogens. We just made one water. And now I can draw a resonance structure of this molecule, putting a negative charge on the carbon. I'm going to just put that down here. So now I have a negative charge on that carbon, and we know that eventually we want to put two hydrogens here because we know the product is propane. So we need to get two hydrogens here. I've got a negative charge. I've got water. So let's go ahead and take that proton from water. Again, another proton transfer. And I'll draw the newly installed hydrogen there. That's a proton transfer. So now I've put one of the hydrogens there, and I can now react with another equivalent of base. I actually just regenerated the base. So I'm going to take this hydrogen off in another proton transfer step. And you can see how I'm slowly starting to get to nitrogen gas on my molecule. And so now I have this anion, and I can draw this arrow push, be loss of leaving group, and you'll see I'm forming an anion at this the carbon that used to be the carbonyl carbon. That's pretty unusual. And I'm forming N2 gas, which is a pretty good leaving group, I think you'll agree. It's gas, it floats away, we can't recapture it. It is an irreversible reaction, so I need to fix my arrows here. This does not go backwards. Right, this is an irreversible step. And that is one reason we can form this very, very strong base. We have the very good leaving group, nitrogen gas, it's gone. This cannot go backwards. And so we're in the presence of water and base, and it's not going to be too much of a challenge. This is also an irreversible step. It's not going to be too much of a challenge for this really strong carbon base to remove a hydrogen from water, regenerating the OH minus, and making propane. And so I need to correct up here. What we see now is that these two hydrogens essentially ended up on this carbon. So all we've lost is N2 gas. So really, we don't form any water in this case. So I'm going to cross off my water that I initially drew up there. We just form N2 as the byproduct. So this is a very interesting reaction because we've formed this very strong base. We've formed a very good leaving group. And really the driving force is the fact that we form nitrogen gas, it can leave, allowing us to briefly form this very strong base, which probably immediately deprotonates water to generate the neutral alkane. So this is the Wolff-Kishner reaction. It does involve the formation of a very unstable intermediate, but again, the giving off of the great leaving group nitrogen gas helps us to propel this reaction forward. And the fact that both of these steps are irreversible also helps us to get to this product.